Section 3.2 is polynomial functions and their graphs. Here's an official definition of a polynomial function. A polynomial function of degree n has the form given. N is a non-negative integer, so we're not going to have powers that are 1/2 or negative numbers. And a sub n is non-zero, all right, that's the leading coefficient. Just a little bit of terminology you probably have seen before. Those numbers in front of the variable x are coefficients, and they can be any real numbers. A sub 0 is the constant coefficient or constant terms, doesn't have an x on it. And a sub n, the coefficient of the highest power term, is the leading coefficient, and that's our leading term. We've already talked a lot this quarter about polynomial functions with degrees 0, 1, and 2. And in this section, we're going to look at higher degree polynomial functions. Just to drill some of that terminology a little bit, here's an example of a polynomial function, or sometimes just known as a polynomial, with leading coefficient 3. 3x to the 5th is our leading term, degree is 5, and the coefficients are listed there as well as the constant term. All right, so just practicing that terminology a little. We want to be experts at graphing polynomial functions, and there are some that we're already pretty comfortable with, including power functions. So just a reminder about the power function f of x equals x to the 5th. I'm not going to do a real thorough graph here, but just a quick reminder, because this has odd degree, it has a shape that's similar to x cubed. As that degree gets higher and higher, it gets a little bit flatter in the middle, but it's got this chair shape. And x to the 8th with this even power looks a lot like x squared, but gets a little bit also flatter in the middle, but has this same general shape. So we're good at power functions already, and if that's true, then we should be able to graph any monomial function. That just means there's one term, using transformations, right? This is just going to be, well, the x to the 5th function, but a little bit skinnier because it's stretched vertically. So just going to be really skinny. I don't have a scale on here, but just to give you an idea. And here I've got both shrinking vertically, so it'll be squattier and wider, and also a vertical reflection. So if we compare it to x to the 8th, that was this guy. Well, it's going to be going upside down, and it's going to be wider this time. All right, so again, I'm not putting a scale in here. We can plot some points to get more exact, but just to give you that idea of how we can graph any monomial function. But what about something like y equals 3x to the 4th plus 2x squared minus 7x plus 1? Quite a polynomial. It's not just a simple transformation of a monomial. With all of these sums of monomials in here, it's not just a simple shift left or right or up or down or stretch or reflect like we've been looking at. So let me just give you a little background, some things we can say for sure about graphs of polynomials. I'm going to give you some facts. Okay, polynomials of degree 0 or 1 are lines, we know that. Polynomials of degree 2 are parabolas. Okay, we've studied all of those. The greater the degree of the polynomial, the more complicated its graph can be. But the graph of a polynomial function is continuous, which just means it does not have breaks or holes. So looking at that picture, that's not going to be what happens with the polynomial function. We should be able to draw the entire thing without picking up our pencil. Moreover, the polynomial function is a nice smooth curve. It doesn't have any corners or sharp points or cusps. So the first one's not a polynomial, and the second two are. So again, you can draw it without picking up your pencil, and it's not going to have those sharp turns in it. All right, we were wanting to look at the graph of y equals 3x to the 4th plus 2x squared minus 7x plus 1. I want to just show you something here. I want to compare it to the graph of y equals 3x plus 4. So y equals 3x plus 4 is the red graph, and 3x plus 4 plus a bunch of other stuff is the blue graph. And let me just play you a little animation here to show you. I'm going to zoom out. And as we zoom out, we can see that even though the graphs are very different close to 0, they start to match up a little bit at the ends. If I adjust my scale a little and keep scrolling out, in fact, they start to become totally indistinguishable at the ends. All right, so what is that telling us? Well, we would say these two graphs have the same end behavior. The end behavior of a polynomial is a description of what happens to the outputs as the inputs become large in either the positive or negative direction. And here's the big claim we're going to make. End behavior is determined by the leading term of the polynomial function. If we look at these examples again, these of course both have the same leading term. And if you think about it, as x gets really, really big, either positive or negative, so that would be at the ends of this graph, these terms start to not make that much difference. They're pretty small numbers in compared to this fourth power. So we're kind of starting to ignore what happens with these slower power terms, and this highest power term really takes over the polynomial. We use special notation to describe the end behavior of a function. So x with an arrow to the right with either positive or negative infinity. These mean x tends to negative infinity or x tends to positive infinity. So let me show you what we would do to describe the end behavior of these functions. In the previous example, we saw that both the ends, the y values, head off towards positive infinity. So I might say as x tends to negative infinity, the y values, well, they get really huge positive. Again, remember the ends of our graph look like this, getting really big positive as we get big negative x's. And on the other end of our graph, as x goes to positive infinity, so really big values of x also yield bigger and bigger and bigger values of y. So here's how I would describe the end behavior for that example. Let me show you another. Let's describe the end behavior of g of x equals 2x cubed minus 4x plus 3. So what I'm going to do is focus on the leading term, that's the highest power. As we get to really, really big positive and negative values of x, those start to not matter so much. And the end behavior as x goes to negative infinity mimics what behavior we have of 2x cubed. And so remember, 2x cubed is just a stretch of our x cubed function. So if I just think of x cubed quickly, as x goes to negative infinity, the y values also go to negative infinity. And as x goes to positive infinity, so looking at big positive values of x on this end, the y values also are getting really big positive. Let's try this one more time. Again, I want to describe the end behavior, so I'm going to look at the leading term and ignore all this stuff, negative 8x to the fifth. This is like x to the fifth. All right, x to the fifth is like x cubed because it's an odd power. But this negative tells me that I've got a reflection vertically, so it's actually going to do this. Well, it doesn't matter what's happening in the middle, but the ends are going to do this, right? That reflection. So I would expect as x goes to negative infinity, the values of y go to positive infinity. And on the other end, as x goes to positive infinity or tends to positive infinity, y tends to negative infinity. The y values get big negative. Here's a little summary. This is in your text too, so you can look at it or you can pause and read this more, but just a little summary of what we've been talking about. Again, feel free to pause if you want to read through that. Okay, well, that's helpful to tell us what these graphs of polynomials look like on the ends, but what about the behavior of a graph near the middle? Here's one thing to think about that we're probably already familiar with. Something that happens in the middle could be x-intercepts. That graph might cross our x-axis. So let me define for you. If p is a polynomial function, c is called a zero of p if p of c equals 0. In other words, the zeros of p are the solutions of the equation p of x equals 0. And we know that when we set an equation equal to 0 and solve, we're really finding the x-intercepts. So those solutions give us the x values of the x-intercept. Zeros are another way to say the x values of the x-intercepts. Here's a little summary of that. All of these are true, and we learn all of this if we solve that same equation, our polynomial equal to 0. If p is a polynomial and c is a real number, c is a 0 of p, x equals c is a solution of that equation, x minus c is a factor, and c, or really should be, I would prefer the point C0, although I took this from your text, is an x-intercept of the graph of P. Let me show you that with an example. To find the zeros of x squared plus x minus 6, I can factor to see what the factors are, okay? From this factored form, we can easily see, well, if we were to set this equal to 0, we get an x value of 2 and an x value of negative 3. That means, well, for this solution, 2 is a 0 of P. X equals 2 is the solution of this equation, sure. X minus 2 is a factor. Yes, we see that. And I could also say 2 comma 0 is an x-intercept of the graph. And those same facts hold true for our other 0, negative 3. So all different ways of kind of saying the same thing. Let's take a look at this function. Now we can say something about the end behavior and the middle behavior. We can find the zeros and determine the end behavior. So let's find the zeros first. And so to do that, I'm going to solve this equation. This factors, let me pull out an x, and that leaves me with a quadratic that I can hopefully factor here. Yeah, two numbers that multiply to negative 3 and add to negative 2. I think negative 3 and positive 1. This has solutions 0, 3, and negative 1. These are the zeros of our function. My end behavior, well, again, I want to look at my leading term, which is x cubed. I can picture in my head the graph of x cubed, and the end behavior of p of x will match that. So this is as x goes to negative infinity, y goes to negative infinity, and as x goes to infinity, y goes to infinity. I'd like to take this a step further and try and use this information to sketch a graph of this same function. So let me just sketch a rough graph. I'm going to sketch in my x and y axes, always label x and y. If I go back here, I learned that I have zeros at 0, 3, and negative 1. Those are also my x-intercepts. So at 0, 0, 3, 0, and what was it? Negative 1, 0. And I'm going to label these to indicate a scale. I have intercepts. I also know my end behavior of my graph, I should expect to look like x cubed. And so I don't know exactly what this looks like, but somehow on the ends of my graph, I'm going to have this behavior. What I don't know is what's happening in between these zeros. I'd expect it might come up and do something like this. Maybe it passes through all three of them, or maybe it bounces off of a couple of them and goes through. I do know that I should be able to draw it without picking up my pencil, so I'm not going to have other places where I jump over the x-axis. It has to only be at these intercepts. There are some different ways to think about this, but here might be one simple way. Let's test some points in between. I kind of know this is going to come up pretty smoothly and pass through the point negative 1, 0, but I don't know if it crosses through or if it just bounces off and stays below my x-axis. Let's try some test points. So here's what I could do is make a quick table of values. I've got negative 1, 0, 0, 0, and 3, 0 already. Why don't I test some points in between, like at negative 1/2 and maybe at 1, and check what their y values are. If I plug a negative 1/2 in here, you can calculate this, but let me grab my calculator and do it. Negative half cubed minus 2 times negative half squared minus 3 times negative half is 15/8 or 1.875. I don't necessarily need to graph this super accurately, but it does tell me that I have a positive value up here in between. So I know that it crosses through. Then when it hits the graph, I don't know if it bounces off again and then maybe bounces off this one, or am I going to be passing through on these? So let me plug 1 in. If I plug 1 in, this one's a little easier. It's going to be 1 minus 2. Let's see, I'll write this out. 1 minus 2 minus 3. Or negative 4, 1, negative 4. Let me plot these 2 points. So negative half about 1.875 and 1, negative 4. If I try to sketch a graph in here, I think I have enough information. I know I'm starting from down here. I have to pass through here to hit that point. I have to pass through here to get down to this point. And this one, well, I know because of my end behavior that I'm not bouncing off the graph. If I did that, I'd have to create another intercept to draw this without picking up my pencil. So I know it must pass straight through this one. And if you want to find a point out here or a point out here, you certainly can. But this looks pretty good. I'd take a minute to sketch this on your graphing calculator and see if this is what you get, but I think we did a pretty good job. Here's just a summary of what we did. We found the zeros of this graph. We did those test points to determine if our graph lies above or below the x-axis on those intervals. And we determined the end behavior. That was enough for us to get a pretty decent graph without going through a lot of extra work to make a whole big table of values. Fairly little work for big return here. Let's try this one more time. Let's sketch a graph of the function x times x minus 3 times x plus 2. It's already factored for us, so if we want to find our zeros, this isn't too tough. X times x minus 3 times x plus 2 equals 0. Well, 0, 3, and negative 2 are my zeros. The end behavior, well, this is a little tricky. This isn't multiplied out, so I have to think a minute about what my leading term is. But I don't think I have to completely multiply this out to see that my leading term, if I did multiply it out, x times x times x, it's going to be an x cubed leading term. And that's going to give me this end behavior. Let me plot my zeros. I've got my zeros plotted. And then let's try some test points out here. I know I have points at negative 2, 0, 0, 0, and 3, 0. Let's go in between, maybe at negative 1 and 1. If I plug negative 1 in here, that's negative 1 times negative 4 times 1. So that should be 4. Negative 1, 4 is a point. And if I plug 1 in, that's 1 times negative 2 times 3, or negative 6. I apologize, it's kind of hard to draw neatly on this, but I think our graph should go something like this. I should be able to draw it without picking up my pencil. We didn't need to do a test point over here or over here because I know the end behavior. So it has to come down this way and it has to go up this way. You certainly can find more test points, but this is enough information. I'd like to make an observation with you. First, a definition. If c is a 0 of p and the corresponding factor x minus c occurs m times in the factorization of p, we say that c is a 0 of multiplicity m. So, for example, let's take the function p of x is x times x minus 1 squared times x minus 4 cubed. 0 is a 0 of multiplicity 1. It would come from this factor, which appears only once. In contrast, 1, which is the 0 that comes from this factor, appears twice. This factor appears twice, so it has multiplicity 2. And finally, 4 is a 0 that comes from this factor, which appears 3 times, so 4 has a multiplicity of 3. Here's what the graph of this polynomial function looks like. I'll label these axes for us. I want to show you a connection between multiplicity and whether our graph passes through that 0 or bounces off and stays on the same side of the x-axis at that 0. Passes through this one, bounces off this one, passes through this one. If you look at multiplicity, 0 is a 0 of multiplicity 1. So let's go over here. Multiplicity 1, and it passes straight through. It kind of looks like a line right here, which would be a function, x is just a linear factor, a first power polynomial function, and it passes through like a line. Multiplicity 2 gives me this quadratic factor, and while I can't tell if it's going to open up or down from the information given, I can tell it's going to have a parabola-like shape at that 0. And similarly, this 4 came from a factor of multiplicity 3, while it's passing through here just like a cubic function. So looking at multiplicity can actually tell you if you're going to pass through the graph or bounce off the graph. And maybe something you can use in addition to test points or even instead of test points to determine the behavior of the graph near a zero. Here's a summary of that we just talked about. If the multiplicity is odd, we're going to have that sort of x cubed or x to the fifth or x to the seventh type of shape, depending on what that value of m is. If multiplicity is 1, it actually passes through in a very linear manner. If multiplicity is even, it's going to bounce off the graph and stay on the same side of the x-axis. Let's use these ideas together to do one more graph. Let's sketch a graph of this function. Let's find the zeros first. So negative x minus 1 cubed times x plus 2 squared equals 0 gives me zeros of 1 and negative 2. And note that 1 is a 0 of multiplicity 3, so I would expect at that intercept that we pass through and hit the other side of our x-axis with a cubic type of shape. This is a 0 of multiplicity 2, so on my graph at negative 2, 0, I would expect the graph to bounce off like a parabola. Okay, we can also take a look at our end behavior, and together with these zeros and possibly some test points, we can get a good idea of what this graph looks like. My leading term is, well, x cubed times x squared. When I multiply an x cubed times an x squared, I get x to the fifth. And the coefficient on that is going to be negative. So I want to think of x to the fifth, but reflected vertically. So here's my end behavior. Let's plot our zeros in here at 1, 0, and negative 2, 0. I can also calculate some test points, but let me just show you. I actually have enough information to tell what this looks like roughly. I know I'm going to start way up here because of my end behavior. Let me grab a different color here. And when I get to this 0 at negative 2, 0, it has multiplicity 2. So I actually know that it's going to bounce off the graph just like a parabola. All right. I need to come back down for my 0 of multiplicity 3 at 1. I could do a test point to kind of figure out a little more what's happening in here, but as I pass through 1, 0, I want it to pass through in that chair shape like an x cubed graph would do. And then I need my end behavior down here. So I could find a test point in between these two, maybe even just quickly find my y-intercept. But even without that, just understanding the behavior near zeros based on multiplicity, we get a fairly good graph. You can check this on a graphing calculator, but it's pretty close.